If there are 50 people in a room, what is the probability that at least 2 of them have the same birthday? What if that number goes to 100? Or what if it's at 20? How do you think that changes? There's a famous problem in mathematics called the birthday problem, and it's from the area of probability theory. Now, you're familiar with probability theory, even if you don't know it. If you've ever watched a movie that has gambling or games of chance or likelihoods or odds, then you have at least some intuition about what probability theory actually is. The problem goes like this. Imagine there are n people in a room, and n is some number like 50 or 75 or 200, but some whole number. What you want to know is how big does n have to be so that the likelihood that 2 or more people share a birthday in that room is greater than 50%. All right, let's restate that problem to make sure that we all are on the same page. Let there be 75 people in a room, and let's say that we're at some campus or maybe we're at a conference, and we can walk from room to room to room to room and go and sample and ask each person, what is your birthday? We want the day and the month. If we can do that 75 times, the question is, how often will we get at least 2 birthdays? And that value gives us an idea of what the probability is for 2 or more sharing a birthday for that given number that we specified. Now for this problem, we're going to exclude leap year babies. Sorry leap year babies, but you're out. Now that leaves us with 365 days in the year. And so we can map the month and the day of the month uniquely to those 365 days. Alright, so if we transfer all of our pieces of paper that represent all possible days into some sort of a tub, what we can do is we can actually simulate this in real life. I'm going to shake them up, lottery style. This will be a sample. Now we have to sample with replacement so that we always have 1/365th chance of pulling a given birthday. First one is 206. Put it back in. Resample. Try not to look at them. 295. We'll do it one more time. 122. And so we can do this repeatedly. So that was one trial where we sampled 3 and we did it with replacement so that everyone had an equal chance of being selected. If we do this continually, that creates a Monte Carlo simulation, which we'll take to the computer so that I don't have to sit here and do this and you don't have to sit there and not watch it. Let's start with a Monte Carlo simulation of 50 people to figure out where the probabilities lie. Whoa. With 50 people in a room, there's a 97% chance that at least 2 of them share a birthday. Now since this value is so high, we should obviously start at 2 people and work our way up. So we'll go up to 25. Based on our simulated numbers, 23 seems to be the magic number where we cross over that 50% probability mark. Now we can figure out the solution to this problem using probability theory. We could go through and count all possible groupings of 2 or more birthdays for the given value of n, but this becomes pretty difficult to count as n increases. Instead we'll use a common trick and count the ways no 2 people can share a birthday. The probability that 2 or more people share a birthday is equal to 1 minus the probability that nobody shares a birthday. And if we carry out this calculation for n equals 23, we find that we arrive right at the value that we calculated with our Monte Carlo simulation, 0.507. And we also note our distributions are rather close. So that was an unexpected result. But what about real life? Does this actually work? The people over at 538, the news agency, collected 2 decades worth of birth data and made it available for free. The Daily Viz created this heat map out of it. Apparently coitus is very popular in December. Here is a visualization of the data. The large spike on day 60 are all of the February 29th birthdays, shifted to March 1st. To perform a Monte Carlo simulation using this data, we need to create a data distribution. We can do this by taking a given day of the year and then repeating it by the total birth count sum. So Halloween, which is day 304, gets repeated 253,673 times. We create an array like this for every single day, glue it together, and then we randomly sample from that glued together array. Doing so for each of our values of n of interest results in this graph, the real data MC simulation, where we've used 1 million simulations per number. Zooming in around n equals 23, we can see the result of our real data simulation, our theoretical calculation, and then our original Monte Carlo simulation. Looking at our distribution with the real data versus the theoretical calculation, we see a very close agreement between both data sets. All right, and the answer is 23. If you have 23 people in a room, then there is slightly more than a 50% chance that at least 2 of them will share a birthday. Now, if you're a teacher or a professor and you have an opportunity to do this, especially if you're a math teacher or professor, sample your room. See if you can replicate these results and put the result in the comment. It would be awesome to actually crowdsource this and see what happens. If you enjoyed the video, make sure to subscribe and take a look at this next video. Apparently coitus is Apparently coitus is very